Hello, I'm Paul Kowalski, and my presentation will be metal dusting in ammonia production. I'm a materials and corrosion engineer here at Equity Engineering Group, coming up on 5 years with the company, and previously I worked with a natural gas transmission company and a valve manufacturer. So real quick before we get into the presentation, just for those who may not be familiar with E2G, we have our mission statement and our goal here. E2G is an employee-owned engineering firm whose focus is on providing specialized engineering consulting services and products for new and aging infrastructure in the refining, petrochemical, chemical, and related industries. We serve all stages of the oil and gas industry, that is upstream, midstream, and downstream. Our goal is to develop and transfer technologies that help clients improve safety and profitability by managing risk and maximizing equipment availability while controlling costs. And you'll see here on the right, another one of our large goals is the transfer of knowledge. So we present symposiums, webinars such as this, as well as releasing a periodic article, E2G Industry Insights, again, just to help the transfer of knowledge. So E2G is really broken down into kind of two parts. First is the consulting side of the business, and you'll see the different business groups within consulting: mechanical and structural, materials and corrosion, rotating equipment, vibration and dynamics, risk-based inspection, process technology, mechanical integrity, and electrical instruments and controls. Obviously won't touch on every group, but we have some of the main offerings from each business unit listed within the consulting side of the business. And we do average about 20 years of experience across all of our consulting business units. And then kind of the second part of E2G is SaaS, or software as a service solution. So we develop and maintain over 750 engineering practices or best practices and over 200 piping classes. And we have clients subscribed to these practices in the oil and gas, petrochemicals, chemicals, fertilizers, and other special industries. Additionally, we offer many software products. We were one of the main developers of the API RBI software. We also provide Sage Plus, Damage Plus, Plant Manager, and we also have a web-based suite of tools on the cloud, and we'll have over approximately 60 apps within this web-based portal as well. And recently, late last year, we acquired Core Solutions, and really Core Solutions focuses on really the statistical analysis and use of your CML or thickness monitoring data, how to interpret it, how to use it to best guide decisions, et cetera. So we are very excited about that as well. And also, we believe in training. We hold many training courses over many different topics and items. Hopefully later this year, we'll return into in-person training again. But for now, we've had success with performing virtual or online training. So that was just a quick overview of E2G as a company. Getting into the presentation, again, metal dusting in ammonia production, we'll provide a high-level overview of the metal dusting damage mechanisms as far as some factors and variables that affect the mechanism, touch on common locations where you may see this phenomenon within ammonia production, as well as some common mitigation strategies and kind of things to consider when approaching this problem. And of course, time for questions at the end. So just a high-level overview of the metal dusting damage mechanism. Really, it's a high-temperature damage mechanism that can lead to catastrophic results or very severe degradation. We've seen damage rates as high as, well, over 1,000 mils per year. So obviously, this is very severe. It initially initiates as really localized pitting, as you can see here on this image, and then eventually really results in just turning the metal to dust, hence the name. So kind of the common factors or requirements for this mechanism to occur, again, high temperature, typically 750 degrees Fahrenheit or higher, as well as a carburizing atmosphere, which is defined as having a carbon activity higher than 1. This high temperature carburizing atmosphere is commonly found in the syngas loop, which is the first step in ammonia production, as this syngas stream contains carbon monoxide, carbon dioxide, hydrogen, and steam. And typically the higher the carbon activity, or that is the amount of carbon monoxide available, generally leads to higher damage rates. And additionally, experience suggests that damage can also be influenced by velocity or turbulence, and consequently accelerating the damage rate as well. So with metal dusting, all alloys are really susceptible to this mechanism. There isn't one material that has 100% resistance, but really the resistance of a material to metal dusting is directly correlated to the stability of the oxide layer. Based on the material of construction, that can be a nickel oxide, a chromium oxide, iron oxide, etc. And really how stable this oxide layer is corresponds to how resistant the material will be. So kind of a brief schematic or summary of kind of the actual mechanism of metal dusting. So again, first, a high temperature carburizing atmosphere is required. So we'll see how here on the schematic on the right. So in this case, it's carbon monoxide, again, which we may find in syngas. It attacks the material, or specifically attacks the oxide layer, and preferentially will go to areas of cracking or imperfection or defects in the oxide layer, and it adsorbs on the surface. So basically the carbon is sitting on the surface. It will then form carbides, and eventually the carbon will absorb or diffuse into the metal matrix, at which point graphite is formed from the carbon diffusion into the material. And then once the graphite forms and you have diffused carbon within the material, it's really an exponential process from there. And that helps explain the severe damage rates that can be observed with this mechanism. You know, again, higher than 1,000 mils per year has been observed. And this is just an SEM image, scanning electron microscope image of the surface of a material that has undergone metal dusting. And kind of the white filaments and, for lack of a better word, blobs are really the carbide formation and the graphite formation from the metal dusting having occurred. So again, just another visual to help understand this mechanism. So recently, in regards to operating trends, the desire for greater efficiency has led to some changes or different directions or goals on the front end of the ammonia production plant, specifically in the syngas loop. And so increased front end pressures, which is resulting in higher carbon monoxide content and therefore increasing the carbon activity, as well as lowering the steam to hydrogen ratios, which consequently reduces the oxygen partial pressure. So the graph here on the right shows the relative stability of several common oxide layers versus really oxygen partial pressure. So as you can see, as oxygen partial pressure reduces, a nickel oxide layer, for example, would be the first to kind of go or not be stable anymore. And as you go further down, additional oxide layers would become unstable as well as that oxygen reduces. And then we can also see from this graph that silicon oxide and aluminum oxide are two of the more stable oxide layers, relatively speaking. And then this graph here on the left is just, again, visualizing this trend and ultimately the results of these trends. So as we move to the left on the x-axis and increase the carbon activity on the y-axis, we're moving into the more severe or catastrophic region for metal dusting to occur. So here's a general process flow diagram of the front end of an ammonia plant. Of course, we have the primary reformer and then the transfer line into the secondary reformer. Again, this is where we would expect the high temperature carburizing atmosphere, and specifically in the secondary reformer, kind of the upper portion of the vessel, we have the process gas inlet nozzle right here, and then we're injecting air at the top. So we're actually getting, or combustion is actually occurring. And based on experience, it appears that combustion leads to, or a combustion environment leads to a more severe metal dusting environment as opposed to, say, in the transfer line where combustion isn't occurring. So this is a very severe spot in the secondary reformer for metal dusting to occur. And typically this would be a 2 1/4 chrome base material. And of course, with the high temperatures, it can be as high as 1800 degrees Fahrenheit. This material is also refractory lined. And then on top of the refractory, there is what's called a burner liner, which is installed to help protect the refractory from any sort of erosion or damage. And that burner liner is typically constructed of an Inconel material or a high nickel based alloy. So several pictures, again, we're in this, well, in this picture, we're looking upwards from this transition section. So we can see the process gas inlet nozzle here, and then up here would be where the air is being injected and combustion is occurring in this region. And we can see the burner liner, which again is an Inconel based or Inconel material. It's intact here as well as in the transition, but here we have exposed refractory, and you can see that the burner liner at this transition location was basically completely wasted or turned to dust, hence metal dusting. So now the refractory is directly exposed to the process. It may be subject to additional damage to the refractory, and then ultimately the 2 1/4 chrome base metal is no longer protected and exposed to those high temperatures, and severe mechanical integrity issues can occur pretty quickly in this case. And here's another picture in the same location of a secondary reformer, but this is not the same vessel. But again, this is just highlighting the damage. In this case, the process fluid or the burner liner was exposed to the process fluid really on both sides. So really the metal dusting rate is double than what it usually would be because it's getting attacked from both sides. And we can see the complete wastage of material here. And again, some damage to the refractory is already being identified, and this can become a large issue pretty quickly for the base material of a secondary reformer. So again, this combustion section in the secondary reformer can be a very severe location for metal dusting to occur. So we've highlighted kind of, what is metal dusting? How does it occur? Where can we expect it, or at least severe metal dusting to occur? So of course, the next logical step is to determine how can I mitigate this damage mechanism? We have several commonly used approaches listed here, and these aren't in any particular order of best to worst, just documenting for information. So like with many damage mechanisms, operationally is when or how you would like to ideally prevent the damage. If you can change something operationally, then we don't need to worry about the damage mechanism anymore. We don't require material upgrades, etc. However, unfortunately, and especially in relation to the recent operating trends for the desire for increased efficiency, this isn't necessarily practical. Decreasing the carbon activity, that's not going to occur because we want that higher CO ratio for better efficiency, or increasing the steam to hydrogen ratio. Again, that contradicts the recent operating trends and the the desire for greater efficiency, so that also won't occur. So in this case, specifically for ammonia production, this strategy is likely not practical. So then the next step, or another common mitigation strategy, may be a material upgrade. Install a material with better resistance, and maybe we won't observe the severe damage. So as mentioned earlier, the resistance of a material to metal dusting is directly correlated to the stability of that oxide layer. So we could choose or install materials with, various elements. We mentioned that aluminum and silicon have some of the more stable oxide layers, relatively speaking. So we can choose a material that is higher in these two quantities, and perhaps the oxide layer will stay intact and metal dusting will not occur. And then kind of a secondary item as well with material selection, there are some elements that actually reduce the carbon diffusion rate into the material. So if we can reduce the carbon diffusion, graphite isn't forming as fast, and then metal dusting won't occur as quickly. This isn't supposed to be a one-size-fits-all approach. Just wanted to highlight kind of some of the items that should be considered when considering a material upgrade for metal dusting resistance. Another very common approach is to install coatings. Based on the environment and base material of construction, there are many different coatings that you could choose. Some being aluminum-based, tin, silicon, etc. And really the goal with the coating is to achieve that stable oxide layer without the added cost of including the high alloying additions into the base material. It may be a lot cheaper to install a thin coating versus upgrading the entire material. And again, the hope is that the coating stays intact, and then the base material is not exposed to the metal dusting atmosphere or damage mechanism. But of course, as with all coatings, surface preparation and application procedures need to be well documented and well maintained to ensure a good quality coating and ensure that it stays intact and there are no imperfections or cracking in the coating. If there are any imperfections, then obviously the base material is exposed and the coating is not doing the job of protecting the material from metal dusting. Another item that needs to be considered with coatings, many of the coatings manufacturers and providers are aware of this, but based on, again, the environment and the chemical composition, the actual composition of the coating may change over time due to exposure to the high temperature environment. So, for example, there are several coatings that rely on basically an optimum nickel to aluminum ratio or nickel to tin ratio. And, following install, that ratio is ideal and will provide the required resistance to metal dusting. But over time, that ratio can actually change through a mechanism called interdiffusion. So, that ratio may begin or may start as satisfactory, but over time it reduces and the coating is no longer protective. So of course, again, the coating providers and manufacturers, they'll add specific alloying elements to really try to minimize or reduce the interdiffusion effect so that the coating stays intact and the correct chemical composition for the entire life of the asset. Another commonly used approach is you can actually inject hydrogen sulfide into the process fluid, and this forms a stable sulfide layer on the surface of the material. If this sulfide layer is intact, then again, it's reducing the exposure of the base material to the metal dusting environment. And of course, metal dusting won't occur then. However, based on the environment and the chemical composition of the base metal, at least one thing that needs to be considered is nickel-based alloys in high temperature sulfur environments may be susceptible to a severe form of sulfidation. And really, this is due to the formation of a low temperature nickel sulfide eutectic. So basically this phase is molten at these operating temperatures, and then the material itself is exposed, and there's no further protection from the sulfide layers. So if you're going to consider H2S injection into a process stream where you have nickel-based alloys, this certainly needs to be considered, and make sure that this form of sulfidation won't occur. This approach has been used with some success in ethylene crackers. However, of course, in ammonia production, sulfur is actually a poison to the catalyst, so this approach isn't practical, of course, for the syngas loop in ammonia production, but nonetheless, it's included kind of just for information and documentation, and try to help for a better understanding of how this mechanism may be mitigated. And then finally, again, as with many damage mechanisms, inspection coupled with fitness for service assessments may help extend the life of the asset, and FFS may be able to qualify the asset for continued service. Of course, this is likely more reserved for lower damage rates. If in a particular case, if the metal dusting rate is 1,000 mils per year or higher, FFS likely won't be able to qualify that. It's just going to fail too fast. But if it's a slightly lower damage rate, FFS may be successful in qualifying the equipment for future service. And then just cited several references used throughout this report. And that is the end of the presentation. At this point, we'll open it up to questions. Thank you.